We talked about conservative vector fields, and now we talk about potential functions. A conservative vector field is a vector field so that it can be expressed as the gradient of some function. So when a vector field can be expressed as the gradient of a function, this vector field is called, again, conservative vector field, and this function here is so-called a potential function. When you have a function and you take the gradient gives you a conservative vector field. When you have a vector field, you can, and you know it is conservative, you can then ask if you can find the function. It's a potential function. Okay, so that's go ahead. And let's see how we can find a potential function. Find a potential function for f being 2xy I plus x squared minus yj. Okay, so first of all, you can check f is conservative. That is checking dy of the x component is equal to ddx of the y component in this case. So this is also equal to 2x. So the equality here tells you that, okay, f is indeed conservative. Okay, that is saying there is a function, let's say f function, f, so that the gradient of this function is equal to the given vector field. Okay, so now that's find f. All right, so from this relationship, we would know that df dx equals the x component of the given vector field, and df dy is equal to the y component of the vector field, because gradient f is the vector df dx, df dy, and f is the vector field 2xy, x squared minus y, right? So we have that. All right, so we're gonna use these two equations here to find f. Okay, so from equation 1, you know that this function f of x can be obtained by integrating the df dx with respect to x. And you can do this very easily. So you're gonna treat y as constant. Okay, so now you have x squared y plus now constant. Okay, so let's think for a second what counts as constant. So an actual constant, like 1, 2, 3, 4, an actual constant is a constant. But also, if you have a function of y, you are also treating this as a constant, right? Because if you have a function for y and you differentiate this function with respect to x, this whole thing will go away because you are seeing this as a constant. So therefore, from the first equation, you know that this potential function should look like something like this. Okay, so this will be constant in the eyes of x. Okay, all right. So now we're gonna use this to compute what df dy would look like. So here df dy becomes x squared because y goes away, plus g prime of y, and then the constant goes away, becomes 0. Okay, so this is partial derivative of df dy you get from solving the first equation, but then from the second part of the equation you also have df dy equals x squared minus y, right? So then you know these two should be the same, so you can set up an equation like this. Okay, so now you want to solve for the g. Okay, so here you have then g prime of y is equal to negative y. Therefore, g of y is equal to an antiderivative of negative y, so that is negative a half y squared. Okay, all right. So altogether, we can write down the function fxy equals x squared y minus a half y squared plus c. Okay, so this is g of y, and then we plug this back into our finding from the first equation. Okay, so this is a potential